field, getting the temperature right, accurately determining the thermophysical and spectral properties of planetary sources.
All right. Thanks, and I'd like to acknowledge my co-authors, Paul Hain, Ben Greenhagen, Pierre Williams, and Dave Page. And I'll just kind of get started with more or less stating the main point or the main points here. And I've got a couple of them, but it's kind of fairly simple. First off, basically the thermal emission from airless bodies is often dominated by effects due to surface roughness and rock abundance. And you've heard that from a couple talks today, as well as Paul Hain's talk yesterday. Surface roughness is a big effect on infrared measurements. And so when you have this surface roughness, you've got shaded and sunlit surfaces. These surfaces are composed of a wide range of temperatures. And the key point here is that those temperatures can't be approximated by a single average temperature. It might work at one wavelength, but it wouldn't work at another wavelength. And so when you assume the single temperature for your surface over your field of view, it will very often lead to very significant errors. And so finally, LRO diviner, so the Lunar Reconnaissance Orbiter Diviner Radiometer, we've been collecting observations for years now, but we've begun a more explicit campaign to really fully characterize the thermal emission from the lunar surface. And more importantly, this can serve as a baseline, so a baseline set of measurements for investigations throughout the solar system. So my message here isn't that the moon's surface is going to be the same as every other airless body surface throughout the solar system, but this is a first set of comprehensive measurements that could be used to serve as more or less a framework for studying these other bodies. Okay, I'll start with surface roughness and make the same point as has been made a couple times before. This is just an astronaut photograph of Apollo 15. This is perhaps not atypical lunar regolith. We've got lots of clods, maybe a few rocks, and it's very, very rough. And so when we're talking about surface roughness from the sort of thermal infrared point of view, this is what we're talking about. It's these sort of millimeter to centimeter scale variations that we see in the surface. And I'm showing a plot here. This is basically a two-dimensional thermal model cross-section. This is work that Pierre Williams put together. You'll see the scale bar here. This is about 5 centimeters. And you'll see the temperature scale here. And this is just a sine wave, and this is 8 a.m., so the sun's coming off from the right-hand side, hitting these surfaces. So these are our sunlit surfaces, and these are our shaded surfaces. And even though they're only separated by a few centimeters, we've got temperatures of 400 Kelvin and 200 Kelvin, just separated by just a few centimeters. And that's because we've got this very rough surface. That surface is highly insulating, and we're in a vacuum environment, so we don't have air to transport heat from the sunlit surfaces off to the shaded ones. So essentially, when we're looking at a surface, especially from orbit, we're seeing all of these temperatures mixed into our measurement, and we can model that. So if we take a roughness model, and so we've got a bunch of facets of different slopes, and we know where the sun is in the sky, and we know how it behaves thermophysically. We can basically calculate the range of temperatures that are in our field of view, take the radiance, Planck radiance from that range of temperatures as they are present proportionally in our field of view, and basically come up with some simulated spectra, radiance spectra. And that's what I'm showing here. And I'm showing it in terms of brightness temperature. So we're taking the radiance and converting it to brightness temperature just based on the Planck equation. And we're going from 1 micron out to a couple hundred microns. And this is basically just a function of solar incidence, at least on the moon. But you can think of this as being at the equator at noontime, 1 p.m., 2 p.m., 3 p.m., 4 p.m., and 5 p.m. And what you'll see is that if we measure the brightness temperature out at 100 microns at 5 p.m., for 25 degrees RMS slope distribution, which is pretty roughly about what we see for most of the lunar surface, we come up with a temperature that's below 200 Kelvin. And if we looked at that same surface at a couple of microns at much shorter wavelengths, we're up above 300 Kelvin. So depending on the wavelength that you look at the surface, you're going to get a very, very different perspective of how warm or cold that surface is. So here's where we bring in LRO Diviner, and I'll make this assertion that it's a very uniquely complete set of measurements. first off, we're in LRO's orbit, drifts in local time. So we can cover basically the full diurnal cycle of any surface on the moon, given enough data collected. The other capabilities, we have a 2-axis pointing capability. So we can look at that surface, not only straight down nadir, but we can look at that surface from more or less any angle. So we can collect data at all times of day from all angles. And then the third key point here is, you can see it in the shading here, Diviner's spectral coverage is actually quite wide. And this is shown in wavelength. We have these visible wavelength broadband channels, which captures most of the reflected solar radiance from the lunar surface. We've got these 8-micron and longer wavelength thermal channels, which collect much, if not most, of the daytime emission, as well as the nighttime emission. So we can collect basically most of the photons coming off of the moon from all directions at all times of day, and that's quite a set of measurements, at least from my perspective. So we'll go back to this plot. And we can use our spectral capabilities of Diviner. So this is just assuming we're looking straight down nadir, and say looking at channels 3 through 5 versus longer wavelength channels, the Diviner's different spectral channels will see a different temperature. And we can use that in order to basically back out surface roughness. There's modeling involved, and it gets more complicated with lots of details, but we could just simply take channel 4 and subtract the brightness temperature of channel 7, and the magnitude of that basically correlates with how rough the surface is. The rougher the surface, the bigger that temperature difference will be. And indeed, we've done that. And the black squares here are the Diviner measurements. And the red lines are basically models for different levels of surface roughness, from 20 degrees to 35 degrees RMS slopes. And you can see that the model with steeper slopes, that you get a steeper curve with a greater difference in brightness temperature between 8 and 33 microns. And you can see that the Diviner data there's a little bit of fuzziness to it, but roughly corresponds well with 25-degree RMS slope distribution. And we've published some of this initial data, I think it was this year, maybe late last year, but some of that results have been published. Okay, so what I've been talking about mostly up to this point are the nadir observations, where we look at the different spectral bands, and we can look at the difference between the spectral bands to get a sense of surface roughness. However, we can also take these multiple emission angle observations. We could take advantage of our pointing capability, so we can measure surfaces from multiple angles at one or many solar incidence angles. And I'm kind of showing this little cartoon here. If you're pointing off towards this direction, you'll see preferentially shaded surfaces, and if we're pointed off this direction in this cartoon, we'll see preferentially sunlit surfaces. So the apparent temperature, the amount of radiance that you measure, will change for a given surface as you pass over it and look at it from different angles. So the two observation types are pretty complementary, and both are being collected by Diviner. And so specifically what I'm calling these surface phase function measurements, where we're looking at a surface from all these different angles, we're starting to collect these data, and we've got a couple of goals here. First off is, kind of as I've been saying or implying, is that we want to define the visible and the thermal infrared phase function as completely as possible over representative surface units with full diurnal coverage, and we can point at a surface both up and down track, as well as cross track using previous and post-orbit observations. And what this will accomplish is it'll characterize the radiative balance of the lunar surface. It will define the phase function of the lunar surface, and the thermal infrared coverage will basically be an unprecedented data set. I don't think that we've collected anything quite so complete prior to this. And there's also significant value in the visible wavelength observations from our visible wavelength channel that will be highly complementary to the LROC data sets as well. In addition to this, we're also in the process of mapping the variations in the surface properties by basically collecting these sustained off-nadir campaigns, where we're constantly pointing off at an angle, and we'll build up a map of the lunar surface strip after strip. So there's a number of benefits to this. The first one, perhaps the most direct one, is that, yes, we're going to get surface roughness at millimeter to centimeter scale. So we're going to basically better understand the centimeter scale surface physical properties of the lunar surface. And that'll tell us a lot about basically the history and the development of the lunar regolith. And if we can see these variations, map them, and tie them back to the process that formed them. But there's kind of more wide-ranging applications too. And for example, this will give us some improved understanding of disk-integrated and limited measurements of airless bodies. So I'm showing a artist's conception of the WISE spacecraft. I guess it's the NEO-WISE now. And when you don't have resolved data of say an asteroid or whatever, you just have a single spectral point, you're basically getting an integration of the entire body. And as you go off to the limb, you're looking very much off nadir, and surface roughness has a big effect on that measurement. And so it's commonly called beaming, and characterizing that beaming is fairly crucial for understanding more or less how large of an object you're looking at. So we'll have a better understanding of how beaming works and surface roughness affects these measurements. Another benefit is improved determinations and understanding of Yarkovsky and Yorp effects. So surface roughness very much causes the surface to emit radiance in a very non-isotropic way. So I'm just taking figures cut out from a paper published in 2012. And if we've got a rough surface, this illustration is trying to point out basically the thermal emission profile is going to kind of lean off towards the sun. And so that little amount of thrust that you get from the Yarkovsky effect is going to be skewed in a certain direction. And in effect, that can have actually a huge effect, especially for lower thermal inertia surfaces. That effect can be basically, it can actually double the strength of that effect. So it can be quite a big factor in terms of these effects. Another benefit is improved thermal corrections for infrared spectroscopy. And now I'm talking about near infrared rather than thermal infrared. So we have a little bit of thermal emission depending on the surface temperature of the body, but on the moon we're talking about sort of off 2.5 microns onward. And you have to correct for that thermal emission. And in this case, I'm showing just an M-cubed spectrum. Got a nice 1 and 2 micron pyroxene features shown here, out to about 3 microns. The original data is shown in black, and this is the official M-cubed thermally corrected data. Now, the M-cubed corrected data assumes an isothermal surface. They derive it from the M-cubed data itself. However, when you factor in roughness and that range of temperatures that you have, when you correct for it, you get this spectrum. You get this very sharp downturn. And when you're trying to interpret the depth of a feature at 2.8 to 3 microns, that's due to the presence of OH or H2O, this roughness effect is a huge, huge deal. It dominates it. And so you have to get this right in order to be able to interpret this well. And it's not that this OH goes away. What in fact happens is that it becomes more prominent than it is in the original data set. And then I think this might be my last example. An additional benefit is this characterization of the radiative balance for improved thermal modeling. And one thing that we're finding, I didn't touch on this too much in this talk or at all yet, but what we're also seeing in addition to this sort of beaming of radiance, we're also seeing a lowering of the emissivity of the surface, regardless of the direction from which you're looking at the surface. And so in effect, the hemispherical emissivity, the emissivity of a surface across the entire hemisphere, is actually quite a bit lower than if you're looking straight down nadir. And so we have actually a lower emissivity of the surface than we kind of thought previously, and that makes it less efficient at radiating out to space, which in effect is an insulating factor in the temperature of the surface. So this effectively results in warmer temperatures both day and night, and so this affects our thermophysical properties. And so the final slide here, and this is essentially my conclusions, is that the Diviner observations can be used to better understand a lot of different things. It's, the applications are quite wide-ranging, and not just on the moon, but throughout the solar system. And understanding these, the effects of surface roughness, how to determine temperature, and how they interact with each other, has lots of applications both to telescopic data sets, current recent spacecraft. Plus, we've got a bunch of thermal instruments on future spacecraft in the next few years. And so I'll leave it at that, and thanks. The M-cubed spectrum, it is from a particular area, but nothing in particular. this effect is, I've run this on different latitudes and whatnot, and basically it's pervasive. This effect is pervasive. You can take any equatorial, certainly M-cube spectrum, and you'll get the same kind of difference between the roughness correction and the original.